Hi everyone, we are group number 5 and today we are delighted to present our article on methods of determination and optimization of bottlenecks in dynamic environment of business processing and manufacturing lines. Our group has put in considerable effort to research and analyze this subject, and we are excited to share our findings with you. In this presentation, we will explore the methods of determination and optimization of bottlenecks in different industries. Thank you for your attention. Let's dive into the key concepts and methodologies that can revolutionize your approach to managing bottlenecks in dynamic business processing and manufacturing lines. The content will be introduction, objective, methodology, result and discussion, and lastly, conclusion. The objective of this study is to define the common issues in any business process flow or manufacturing lines. Provision of solution that will resolve the queuing or bottleneck. Upon generation of solution, measure the cycle time or processing time before and after the implementation of the corrective action. And lastly, to generate a common theory on the bottleneck and its solution. Moving forward, Erwin will be presenting the methodology for electronics manufacturing.
Thank you, team, for handing me the presentation. For my side, I'll be presenting the electronics manufacturing. The process flow is, as mentioned here, you have the material queue, SMT component mounting, the PTH or ERSA soldering, and then finishing, which is the end process as a sample of our study. Processing time for a batch is at least we have these four entities. We got M sensors, TC hubs, LS controllers, MS controllers. Process steps are, as I mentioned, are the material queue, SMT, PTH, and finishing. For each entities, which are the M sensors, TC hubs, LS controller, and MS controllers, they have their own processing time. I made the material queue infinite for the purpose that all the materials are coming, assuming that it's continuously uh, coming to manufacturing. And even the finishing, I did not put any timing at all because it goes to the next station. So I got three scenarios in the manufacturing simulation. So we have the first scenario, which is the standard line, which has all the machine, just one machine on each processing steps. Okay. For scenario two, I do have the raw material has two locations. SMT has two locations, and PTH is the same, and finishing is also the same, one location. For scenario three, I have one location for the material queue, and for the SMT is only different because it has a three machines location. Okay, so running the promodel approach for scenario one, the problem occurs when the LX controller and the MS controller not able to process, but it was stopped on the processing of the hub. Okay. On the scenario two, so meaning I do have a bottleneck. The bottleneck is identified as the SMT process. So from here, I would like to do a simulation. What if I put a 2Q location and and two SMT location? So what happened here is that I have successfully managed to process all the entities, which are the M sensors, hubs, and the controllers. On scenario three, I also successfully processed the all entities, but and you can see here that the last processing is the LS controllers. Okay, so now between scenario two and scenario three, which are both successful in running the three entities, I would choose the scenario two because of the minimum investment cost. While in the SMT, I do need three SMT machine. At the same time, you can see here the idle. There's a lot of idle for if ever I have three machines for SMT.
So with regards to methodology for airport security, security checkpoints at airports are specific area where passenger and their belongings undergo security screening before boarding their flights. These checkpoints are designed to ensure the safety and security of air travel. Here are the typical security checkpoints at airports. Document check, from document check to security, additional screening, and lastly, post-security. These security checkpoints are vital for preventing prohibited items, weapons, and dangerous substances from being brought onto aircraft, thereby ensuring the safety of passengers and crew during air travel. Moving forward to methodology. As shown in the image scenario 1, basically there's only one security lane available for all passengers to go through. So this creates a bottleneck, especially during the peak travel times, causing long queues and delays for passengers. While in the image scenario 2, basically there are several security lanes available, but some lanes may operate more efficiently than others due to factors such as staff availability or equipment malfunction. Passengers may face a bottleneck situation if they end up in slower moving lane. And the last image scenario, some airports offer pre-screening programs where passengers can go through an expedited security process if they meet certain criteria such as pre-check or clear. However, if there are limited lanes or resources dedicated to these programs, passengers not enrolled may face longer queues and bottlenecks. So the best solution scenario among the presented option is implementing pre-screening programs like pre-check or clear. So these programs allow eligible passengers to go through an expedited security process, reducing the load on regular security lanes and preventing overcrowding. By dedicating specific lanes or resources to pre-screening, airports can optimize efficiency and better manage the flow of passengers, minimizing the likelihood of bottlenecks occurring. Additionally, the background checks and vetting processes involved in pre-screening enhance security by identifying low-risk passengers beforehand, allowing security personnel to focus on those who haven't been pre-screened. Ultimately, this leads to shorter wait times, smoother security process, and higher level of satisfaction for passengers, contributing to an overall improved travel experience.
A time and motion study was conducted among 30 samples. Shown in the slide is the step-by-step process of warehouse replenishment, along with the average time it takes to complete each step. So the warehouse replenishment process is a three-step process which starts from the removal of pallets in the bulk location or storage racks to the placing of these pallets in the pick phase, ready for picking and dispatch for outbound. There are 4 people working on the process: the replenishment team leader, 2 reach truck operators, and 1 pallet mover operator. To better understand, here is a visual guide of how pallets move during the replenishment process. The figure on the left shows the simulated layout of a warehouse replenishment process. The input location is the bulk location or the storage rackings where stocks or orders are received and taken from. The staging area is a transit location for the stocks before they will be placed in the pick phase locations. In this figure, 4 stations are identified. Each station is assigned a corresponding downtime to simulate multiple possible scenarios. Station 1 has a clock downtime, which simulates the downtime during manual deployment, such as the printing of papers and the planning of task distribution. Station 2 is for the usage downtime. This simulates the delays caused by the reach truck and pallet mover units, such as the recharging time of their units. Station 3 represents the entry downtime, which denotes the delays due to location cleanup, such as organization or repalletization in the peak phase locations. Lastly, Station 4 does not have downtime, since this would represent our overflow locations should there be no more space in the first 3 stations. Now let's proceed to the results. For scenario 1, this figure This figure shows the time distributions of each location in terms of operation time, setup, idle, waiting, block, and downtimes. In this first scenario, it can be seen how Station 2 contributes the most to the downtime percentage, followed by Station 1. Now, the downtime for Station 2 is due to recharging purposes, which we cannot easily control since the units should really be charged after a certain period. Station 1, however, can be controlled through automation, since the delays are brought about by manual deployment, like the printing of papers and the planning of distribution. Now, scenario 2, this simulation shows the time distribution once Station 1 downtime are eliminated, wherein the deployment process is fully automated. This gives no allotment for manual printing of replenishment stocks, manual distribution of stocks, etc. Now, comparing the two scenarios, it can be seen how the removal of Station 1 downtime, the clock downtime, increased the productivity from 285 to 299. Consequently, the average time in the system and in the operations improved as well.
So good afternoon, sir. I am Bill, and for today I will be discussing the exam approval system. And in this slide, we will be discussing the process. So the process is that I designated um, the professors with 1 to 9 as their identification, and then once that they had created the exam, it will be submitted to the review panel. Then next, after the review panel has seen or verified the questions, they will be submitting it to the department head for approval. So there are some pointers that we need to include with this simulation. So the first one is the process involves the following. So the reviewers have a unestablished probability where either they accept or reject the questions from the professors. So this will be the variation, one of the variations when we conduct the different scenarios. And at the same time, the process takes about 4 hours per week throughout the whole semester. And lastly, the department has 100% approval once the reviewers already endorse the exam. So these are the limitations to these simulations, and we will be discussing with the promodel observations. So after the promodel result in scenario 1, we observed that with the moderate pace of question creation, each professor contributed one question every 20 minutes, resulting in a total of 3 questions per hour. So despite the meticulous process by the reviewers, of course, the department head's approval remained at high at 100%. However, there were concerns regarding the high idle time of reviewers, prompting a recommendation to increase the capacity of the professors per hour to streamline the process. So moving on to scenario 2, we note that a past surveys of question creation with 5 questions generated per hour by 9 professors. So this means to say that the review process remained thorough, with each question receiving 10 questions of dedicated review time. Impressively, of course, still, the department had maintained a 100% approval rate, while reviewers maintained a commendable 90% approval rate. So despite the high approval rates, concerns arose regarding the potential discrepancies in the exam content due to rapid pace of creation, leading to a recommendation to increase the review per time per question. So finally, in scenario 3, we observed an intensified exam creation process with 10 questions generated per hour at the same 9 professors. So reviewers dedicated a substantial 20 minutes to review each question, resulting in a notable decrease in idle time. While the reviewers maintained 70% approval rate, the department head is still, of course, at 100% approval rate. So the increased volume of questions generated per hour enhanced the probability of capturing the learning objectives of the course involved, of course, and reflecting an optimized workflow and quality assurance in the examination creation process.
Now, moving on the commonality of the bottlenecks among the four industries, which are the Industry 2, Industry 1, Industry 2, Industry 3, Industry 4. So there is an insufficient resource manpower, lack of technology, okay, training of personnel, process insufficiencies, and resource constraints. Okay. For commonality of solutions among the four industries, what we had is addition of process stations, new technology, which is for Industry 3, training additional personnel to make the process efficient, additional resources allocation, guidelines clarification, and streamlined communication, as mentioned in the Industry 4, which is very specific, increasing utilization, which is Industry 2 and Industry 3. Conclusion. Time to produce a product or complete a service has a direct impact on solving the bottleneck. Solutions can be addition of process stations or improvement of processing time, splitting the process steps, or adding parallel similar process steps at the bottleneck can provide a capacity. Queuing is not a solution, but it's a delaying system in order to accommodate other entities. It can be another bottleneck entities that has to be invested through another facility or splitting the process. That's all for our presentation. I thank all our team for making this happen. I hope you like it.